Okay, so let's take a look at calculating probabilities with our normal distribution using Excel. So the setup of these problems will have some bell-shaped curve. They'll say the data is normally distributed, some sort of information that leads us to our bell-shaped curve. So peak in the middle and then short on either side. Okay. And then part of the definition of this normal model, they'll have to tell us the mean and standard deviation. So we'll have something for the population mean and population standard deviation. So this gives us the distribution of our model. So our random variable x is defined by a normal model with some mu and sigma, or mean and standard deviation. Then with that setup, so knowing we have a bell-shaped curve, knowing the mean and standard deviation, we can start asking questions about what's the probability of having this cutoff value or some other cutoff value. What's the probability of being larger, smaller, between, those types of questions. So this is going to relate to the area under the curve. So in terms of having some endpoint, I typically refer to that as a cutoff value. So that's basically going to stop the area at some point that we're shading. And then we can be shading to the left, we could be shading to the right, or we could be shading in between two values. So those are kind of our three scenarios. Within Excel, we'll just have one function, but we'll need to switch how we use that function based on what scenario we're working with. It's similar to what we had to deal with the binomial model, because this normal distribution function within Excel only uses area to the left. So we need to get kind of creative with complements and differences in order to find what we're looking for. So while we're asking questions about probabilities or percentages, you want to think of this as an area under the curve. So the first scenario, if we're calculating area to the left, so this is a scenario of looking for less than or equal to some cutoff value, less than or equal. It can also just be less than. So something that's different from our binomial model is that having equality versus not having equality, so it being less than or equal to versus just less than, there's no difference under the normal model. So if it just says less than or equal to or less than, we use the same calculation. Then there's the scenario for area to the right. So this would be if we're looking for more than or equal to or just more than. And then our third scenario is looking between two values. So we'll have a smaller value and a larger value. So this area to the left, we're going to type into Excel equals norm.dist. So normal distribution. Then it wants 4 pieces of information. It wants this x value, which is our cutoff, which is stated in the question. It's the value that we're looking for, like less than or equal to 24, or less than 24. We would type in 24 right there for x. So we want to list x. We want to list the mean, the standard deviation, and then this last piece will always be writing true. The question that Excel is asking there is whether or not it's cumulative. And for us, it will always be cumulative. So it's making this whole area, in this case, to the left. So this scenario is where we have our bell-shaped curve. We have some cutoff x somewhere on our number line. And this would be the case of looking less than that value. So we would be shading to the left-hand side. Okay, so if we want to do area to the right, so more than or equal to, so this would be the case where we have our bell-shaped curve, we have some cutoff value x, and we're going to be shading to the right. We want the area under the curve to the right-hand side. Now, like I was saying, this norm.dist, normal distribution function within Excel, always works with area to the left. So in that first example, we didn't have to do anything special to it. This one, since we want area to the right, we just use the complement rule. So we would do 1 minus that area to the left. And then whatever's remaining gives us the exact area we want. So for any case of more than or greater than, you'll have this 1 minus and then that normal distribution function. Same thing, you'll have your mean, your standard deviation, and we'll always be writing true right there. And then for this last scenario, I didn't leave myself very much room here, but let's try this out. We're looking between two values. So one value will be small and one value will be large. And we want to find the area between those two values. So what we're going to do is use a difference. So you're going to use that normal distribution function with the large value, because what that will be doing is taking this big area to the left of the large value, but it has too much information. It would have this tail that's to the left of the small value. So we want to get that out of there. So we subtract out this normal distribution using the small value, same mean, standard deviation, true. All right, so let's see these in practice. So we're going to go back to those examples from example 1, where we found those probabilities using the empirical rule. We want to get away from the empirical rule because those are just estimated values. So we want to find these exact probabilities, but what we should be seeing is pretty close. And that's where the empirical rule is kind of nice. It can give you an idea of what to expect in your solution, but we want to use technology to find that exact answer. So I'm just going to write down those probability forms here. So the part A was the probability of being between 32 and 48. And part B was the probability of x being greater than or equal to 48. C was the probability of x being less than or equal to 24. And D, probability of x being less than or equal to 54. Okay, so we want to get probabilities out and we're going to use Excel. I'm going to go ahead and write on the page what I'm going to type into Excel. So this part A, looking between two values, is definitely the trickiest to input, so why not start there? So first thing we need to notice is that 32 is the small value, 48 is the large value. So what we're going to put into Excel is this difference of the large value minus the small value. So I'm going to type into Excel as equals norm.dist, listing that large value of 48. The mean, oh yeah, let's redefine our distribution here. So this distribution for a random variable is normal with a mean of 40 and standard deviation of 8. So back to my notation, norm.dist 48 comma, and then I'm going to list the mean and standard deviation, and then I'll type in true. And then I'm going to subtract the same notation, but with a smaller value. So norm.dist with the 32 as the x value, but mean of 40, standard deviation 8, true. That should all work out. Okay, let's go to Excel and see how this works out. So equals norm.dist 48, comma 40, comma 8, comma true. And then minus norm.dist, normal distribution. It's kind of weird to say that out loud. So 32, comma 40, comma 8, comma true. And equals, and there's our 0.682, and then we'll round to 7 there. So 0.6827, so that's a 68.27% chance. All right, the order is important there. Make sure it goes the larger value then minus the smaller value, since that's how the areas need to work together. Okay, part B here, so we're looking for P of x is more than or equal to 48. So this is an area to the right-hand side, so we're shading above. So this is where we need to use the complement. So we're going to go 1 minus, and then we're going to go norm.dist. Our x value is that 48, mean of 40, standard deviation 8, true. All right, so in Excel, equals 1 minus norm.dist 48. and 48 true. And there's our 0.1587. So 15.87% chance. All right, part C, P of X is less than or equal to 24. There we go. So this is area to the left-hand side. So this is where we can just use that normal distribution function without anything extra going on. So I'm just going to go equals norm.dist and list 24, 48, and true. And the calculator should return a 0.0228, so 2.28%. So for less than or equal to, nothing extra to type in, just the normal distribution. Part D, probability of X is less than or equal to 54. So same scenario, we're shading to the left-hand side. And with that, we'll just type in equals norm.dist. X value 54, mean of 40, standard deviation 8, and then true. And that should return us with a 0.9599, so a 95.99% chance. All right, so now let's look at a different scenario. So we have this medical study of the population of children in Wisconsin were found to have serum cholesterol levels that were normally distributed with a mean of 1.75 milligrams per milliliter and a standard deviation of 0.3 milligrams per milliliter. So first thing we're going to do is define and draw the normal model for children's cholesterol in Wisconsin. So if this children's cholesterol level is our variable X, it is defined by a normal model, so my capital N, parentheses, and then I'm going to list the mean and standard deviation, so 1.75, comma, 0.3. And I'm going to draw a bell-shaped curve to the best of my ability. There we go, not too bad. So right in the middle, we're going to put the mean of 1.75. And then I'm going to go 2 standard deviations above, 2 standard deviations below. That tends to get enough information going. And again, just try to estimate where 1 standard deviation above and below is. So we'll just get our number line going. And what we'll do is, let's see, moving to the right, we'll be adding 0.3. So this is a 2.05 and then a 2.35. And then moving to the left, we're subtracting, so 1.45, 1.15. What I also like about this drawing, where you have the mean in the middle and then going 2 standard deviations above and 2 standard deviations below, is you get an idea of the scale of the values and what's kind of expected. So what we end up saying is that to be within 2 standard deviations of the mean, that's kind of expected for our data. To be beyond that is extreme. So I get this idea that 1.15 to 2.35, those are expected cholesterol levels for this group. To have anything come through that's above 2.35 or below 1.15 would be pretty extreme. Okay, so we have a child has a cholesterol level of 2.11 milligrams per milliliter. What is the percentage of children? So we're looking for a percentage. And what can be really helpful is whenever you see percentage or probability with these normal model scenarios, you're thinking area under the curve. So what is the percentage who have cholesterol levels that are higher than this child's? So looking for higher values, so we're looking for more than, so larger. So we're looking for the probability that X is more than or equal to 2.11. Again, even though it's strictly saying higher than, really we can just think of it as higher than or equal to, because the difference between being more than 2.11 on a number line versus being at 2.11, there isn't a difference in the probability. So we can just assume we have equals there. Okay, so we're doing area to the right. We have this cutoff at 2.11. sets between our 2.05 and 2.35 values on our graph. So I'm just going to estimate. There's our 2.11, and we want the area to the right. So in Excel, I'm going to use the complement since we're using area to the right. So I'm going to go 1 minus and then norm.dist. And we have our x value of 2.11. Mean is 1.75. Standard deviation is 0.3. And this is cumulative, so we write true at the end. Okay, let's go to Excel. So equals 1 minus normal distribution, 2.11, 1.75, 0.3, true. And we get a 0.1151. All right. 0.1151. And then we want to answer with a nice sentence answer. So the question is, what is the percentage of children in Wisconsin who have cholesterol levels that are higher than this child's? We can say 11.51% of children in Wisconsin have cholesterol levels higher than 2.11 milligrams per milliliter. All right. Find the percentage of children in Wisconsin who have cholesterol levels between 1.3 and 2.23. So we're looking between two values here. So let's see, 1.3 is the smaller, 2.23 is the larger. So in Excel, we're going to need to use a difference. So it always goes the larger minus smaller. So we're going to go equals norm.dist with the larger value of 2.23, mean of 1.75, standard deviation 0.3, and true, minus the normal distribution with the smaller value. So the 1.3, 1.75, 0.3, true. All right, let's go ahead and type all of that in. Sorry, I know it's kind of redundant to write it on the paper and then type it in Excel, but sometimes this is pretty small here, so hopefully it's easier to see written out. So 2.23, then 1.75, 0.3, true, minus norm.dist, 1.3, 1.75, 0.3, true. And we get 0.8784. 0.8784. So we could say 87.84% of children in Wisconsin have cholesterol levels between 1.3 and 2.23 milligrams per milliliter. All right, so that's finding areas under the curve using Excel, whether it's area to the left, area to the right, or area between two values. We just need to change our notation a little bit so that it's calculating the correct area, all based on areas to the left.